So what you have here is a pump system. The manufacturer is Amatrol. The model number is 950-PM1. So the pump, entire pump is here. We talked about centrifugal pump. This is the centrifugal pump. This only this portion attached by a electric motor. So to drive this pump, you need a motor, and through the shaft, the impeller. I think you saw how the impeller and convolute is there, and again, the fluid comes in the center of the pump and then get discharged to the circumference of the pump. Okay, so given that, let's understand the whole system here. What we have here. So there is a tank where the water is stored, and this is the suction side of the pump, where as the pump is running, it is drawing a vacuum, and that vacuum is bringing the fluid inside, and that fluid is going into the veins of the pump, gets the because the rotation, the the energy is important to the fluid particles, and those the the fluid has certain flow rate and also the pressure, and going to the downstream of the pump. So this is the upstream, this is the downstream, and then from that system you have a maze of tubes connected here. The purpose of this setup was to do a lot of different things, to measure the friction in different sizes of the pumps, but that's not our goal. We're going to be doing only the pump characteristics using this system. So these valves, the way it is done is kind of forked into multiple paths, but we'll be using this main path of this. So that means you could literally close these valves. We don't need the use for it. That means no flow is coming out, only all the flow is going from here and going to this is the main valve we'll be regulating. So that means we wanted a completely open, 75% open, 50% open. So these valves is what we're using to control the amount of flow that we wanted to go through the system. And then what we also have here is a control unit. In the control unit, you have start, stop, and also you can regulate the speed of the motor. Remember this motor we have, you can change the speed, this motor, to change the speed by this knob here. So you can go in a percentage mode or just measure the hertz. The speed of the motor is measured in frequency, which is hertz, and that's what the data it will be collecting, and that is the main function of this box. So then, as the fluid is going through, there is a flow meter. We have a digital flow meter. Remember a rotameter we talked about? For this one, we're not using the rotameter, but we're using a digital flow meter, which is gallons per minute. That's measuring in gallons per minute. So that is that way we can keep track of, as we're increasing the speed, what the flow is, and so on and so forth. Okay, but along with it, there are a few things also there. Now, if you look at it, there is a lot of pressure gauges here, and then there are two connections to those pressure gauges. So one is a suction. That means, remember we talked about cavitation. The vapor pressure of the suction side of the pump should be above than the vapor pressure of the liquid, whatever the liquid, if it's a freon or if it's a water, and if it's a gas, it has to be less than that. So this pressure gauge is what is going to measure. And then downstream pressure, that means as the fluid is coming and you're running at a certain speed, you're developing some pressure. That pressure is measured by the discharge side. Okay, so this is the suction side, the white tube, and this is a kind of a yellowish color is a discharge side. So that means how much pressure the pump has developed. That's what you're saying. So our lab consists of a lot of things. First, we'll do the basic things: flow versus speed, and also flow versus valve closer, but it's now the advanced level would be to measure the discharge pressure also, both suction and discharge. So then if you add the suction pressure to the discharge pressure, we call it total pressure. So discharge pressure is one and total pressure is another one. I'll show you the graph. So let's go step by step. First thing we'll do is to start the pump, you push that button and you control the speed, and you can go from 0 all the way to 100%, but 100% is equal to 60 hertz. That is the maximum speed of the pump is 60 hertz. So we'll just back off for time being. So while you're doing that, immediately what happens is all the flow is going through the pump, you'll see the readings on the flow meter. So bring the camera close to it, I'll show you. So here it is, you see some number there. If you get our focus there. So now as I increase, the number changes because I'm increasing the speed. I don't know if you can see it or not. The maximum speed on that equipment is like a 22 gallons per minute, 22, 23 gallons per minute. So that's how the speed, as you increase the speed, the flow goes up. So that's as simple as that. Okay. So one experiment is you're running the speed at different levels, like at 10 hertz, 20 hertz, 30 hertz, all the way up to 60 hertz, and you're recording what is the flow is. So that way you're developing a relationship between flow versus speed. So let me show you the graph, how the flow versus speed graph look like. And here is a graph. So if you can see, flow on the X along with it, the speed increases. That's one experiment. And the second experiment is you go to the maximum speed. Now I'm going to the second experiment here. You go to the maximum speed, which is 60 hertz. And then you slowly start closing it down. This is 100% open, and then go to 75% open. So 100% open, you record the flow, and you 75% record the flow again. And then you go to 50%, you record the flow. And you go to 25%, record the flow. And you go to completely closed, you record the flow. So you're developing a relationship how as you are closing the valve at certain speed, how the flow is changing. So that's the second experiment. So coming back on the graph chart of it, how it looked like, here is an example of that experiment we have done. So what you have here is, again, flow on x-axis and percentage of the valve opening, right? So 100% opening versus 75% opening, up to 25, or so on, so on, so forth, going down. But look at the behavior, how the flow is. See, it's not a linear line. It is, it has its own shape to it. Okay, so that's another graph, another experiment you're doing. Okay, so now the third experiment, we'll come back to that in a minute, is since we have done two experiments, we're merging them together. Okay, you got one graph with a flow versus speed, and then you have another graph, flow versus percentage of valve opening. So what I have done here is, on y first primary axis, y-axis, you have flow is a speed with hertz, and then on the secondary y-axis we have percentage of valve opening. That means I combined both the graphs, but whereas x-axis remains the same. So since you have the two data point, that you can see the relationship, how they are connected, between valve opening or so. So the third experiment is where we'll be doing some head calculation, pressure measurement. So how do we do that? So as I also, one more thing I wanted to add on to is, remember the first graph, we did it 0 all the way up to 60 hertz. Now for the percent of valve opening, we kept the speed constant 60 hertz. but we can change it to 45 hertz and collect the data. 35 hertz, collect the data. So you can have multiple graphs, right? So our third experiment is we'll be doing that and also measuring the pressure. Let's talk about how to measure pressure. So for example, right now I have for example, let's say 60 hertz, 75% opening, the valve opening, I'm measuring a pressure on the suction side. This is when you say it's a negative pressure, obviously. So this is measured here in vacuum, and there are two measurements are there. One is inches of mercury. So uh, you have to read the graph carefully. Maybe we'll explain it separately on that one. But you have two scales: outside scale, inside scale. So make sure you use the right scale, and whatever it is, that is, you can see the negative numbers here: -1, -0.8, so on and so forth. So lowest vacuum, I mean zero is here, and then slowly increasing the vacuum here, and it comes to the. So at this point, it is the maximum vacuum that this gauge can record, right? And then if I change the speed, that number changes also. Just focus on the camera for a second. See that how it's changed? All I did was change the speed. As I increase the speed, it goes maximum value. And if I open the valve completely, and you know, you see some more increase, small increase, but you have, so that is behavior of the vacuum. While we're doing that, we can also measure the pressure downstream. So again, there are two scales are there, inside, outside. Doesn't matter which scale you use, and one is one scale is bar, the other one is kPa, and here inside scale is bar, the other one is inches of mercury, and also three gauges are there. Why is the purpose of three gauges? The purpose is to measure, depend upon how much restriction you have, you're using a different gauges. If you want a very precise measurement at low flows, you can use this. And if you are using a full high pressures, you can use that. But most of the work for us, we can use the center gauge. So these two can be taken out and inserted into immediately without. While it's running, you could still do that. So that is the flexibility we have with this one. Okay. So now the third lab, what we're doing is, as we're 100% open at 60 hertz constant speed, and you're recording the vacuum and also the pressure. So if I change to, let's say, 50% valve opening, so you can see the numbers change. See how the pressure vacuum gauge change and how this pressure gauge change. So you are recording those. So here, whatever the readings are, either inches of mercury or kPa or psi, all has to be converted into head. So use the conversion factor. So now we do the plotting in feet. Uh, so uh, that's the purpose of that. So that's why the feet makes easier to analyze and evaluate the systems. So that's why we are using the pressure head as a unit of measure. So one more point I want to show it to you was, if I drop down the pressure valve opening, that means I'm closing. So that means only 25% of the valve is open at this time. You can see the vacuum has changed significantly and the pressure has gone up. So this is the relationship you are developing. So you are doing for 60 hertz now, and you're going to do the same thing for 45 hertz, and then you do the same thing for 35 hertz. So when you do that and you calculate, now you have to make sure the head for the vacuum and everything converted into feet feeds. So then you do the plotting. I'll show you how the plotting looks like. So the plot, when you come here, the plot is, here is the experiment we have done. You have three different curves. Again, x-axis is flow, gallons per minute, and the y-axis is in head. We're talking about downstream head. Okay, the vacuum head is not added into this, only the downstream head. So you can see when the flow is zero. Remember that graph I was showing you? When you're zero flow, the maximum head. See that here? For example, let's just take the 60 hertz. Maximum head is here. And as the flow is increasing, the head drops. So that's the relationship we're trying to find out. Okay. So now that is for the 60 hertz. But if you go to 45 hertz, it goes down. Why it goes down? Because there's not enough kinetic energy. So it's not able to build the pressure it needed to build. So that's why the head drops. And if you go to 35 hertz, and if the kinetic energy is even lower, and that means the momentum is lot less compared to the 60 hertz, and then the graph. So you see a similar, but they are not linear. They are, they have their some mathematical functions to the shape of it. So now, once you have all this data, you can also calculate the total head the pump is generating. That means, what is total head? Total head is a combination of pressure head and suction head. So that is another graph I have. I'll show it to you. And once you have done there, and this is the total head. That means you are adding both heads together. And this one is done at speed of 60 hertz. Remember the 60 hertz data you collected? For that data, you add the suction head, pressure head, and then that becomes a total head. Again, always remember, you're collecting data in inches of mercury for suction, and you're collecting the data in PSI. All has to be converted into feet. So that then add together, and this is what you're going to see. So this includes all the graphs that is related to the centrifugal pump. Okay, so probably one more thing I want to add on is, remember I was talking about efficiency. So what we said was water head efficiency. Whatever the amount of volume of water it is developing, what is the pressure is developing, that is this portion, and the motor efficiency is the brake horsepower. So brake horsepower, water horsepower. The ratio of those two is the efficiency. Got it? So at least you know the relationship. Other thing is, you have to be careful in this tube when you're flowing. We want to make sure there's no bubbles in it. If they have the bubbles, means that pump is not primed properly. The priming is another element. What is priming? In the suction side, you want to make sure that all the bubbles or everything is done. And when it is done, that's when it draws the fluid, and you see a steady stream of fluid coming in. Otherwise, you'll have wrong amount of flow and pressure develop when you have bubbles into the system. So that's one precaution you have to do. To do that, make sure you have enough fluid in there, and it is not drawing any water into the system. And these are the precautions you have to take. So when we do the lab, we'll explain a little bit more. But generally, I'm giving an idea how this lab is. So there are two different labs. We're going to do it. One simple stuff in the beginning, and the other one is going to do the pressure head calculations. Okay. All right. Thanks.